Alright, so here we are with our last chapter, chapter 6, and now we're on section 1, which is about vectors in the plane. And you should have been exposed to some vectors in Algebra 2, but we are further exploring. So, here we are with two-dimensional vectors. Two-dimensional vectors are an ordered pair of real numbers that represents a direct distance. And two or more vectors whose sum is a given vector are called components. So, your standard representation of a vector is going to be an arrow, here we are, from the point of origin over to the point that it meets it. And the component form of a vector, again called components, uses the angled brackets. So again, this is kind of these brackets instead of your parentheses. It uses this notation to represent the horizontal and vertical components of the vector and does not necessarily start at the origin. So the interesting part about these is that you can actually have them start over here, for instance, but it must be that same direction over and up from this point that was made. So really, when we think of this type of vector, A ends up being the horizontal movement, which is normally what it is, the over. And then the B is going to be your vertical movement. And again, that's up or down based on wherever it is you started, which doesn't have to be the origin. So just so that we have that. This one here, looking at our example, we notice that U and V are the same vector, and they are represented by an equivalent arrows. So you go over 4 units and up 2 units in order to get to the end of that arrow, and since that's for both of them, they are equivalent vectors. Also, one thing to note in here, if you do not remember it, is that vectors are bold letters. And so because of the fact that you can't necessarily do bold letters, you can also, other than doing a bold letter, you could also do a regular letter with half of an arrow. So again, for your notation, both of these work. Just depends on if you're typing and have the ability to do bold or not. Alright. Our next one here is your head minus tail rule and an arrow with an initial point of this. So we're saying that that's this point here, maybe at the origin, and a terminal point where that arrow is going to be over here at x2, y2. All you need to do in order to represent the vector is take its slope, a change in y over change in x, right? Or just take those values, subtract them, take the y values and subtract them, and now you have your vector itself. So what we're going to do here is this example, which says that we're going to use the head minus tail rule to prove that u and v are the same vector. So I just want to draw your attention to our formula sheet because it does have the head minus tail rule on it. It does also talk about the fact that our initial point is this one, our terminal point is this one, and of course C in bold is AB with those bracketed parentheses around it. So if you need to reference that later, it will be on your formula sheet that's given. So in order to do this, let's see, we need some coordinates. So this one here is going to be 1, 2, 3, 4, 5, negative 5, 1. And this one here is negative 1, 3. And so in order to get vector u, or its coordinates, I'm going to need to take my x's and subtract them. So let's see, initial point is this one, and this one is the terminal point, where the arrow is. And so I'm going to take the terminal point, which is an x2 of -1, and subtract the initial point, which is -5, and put that in with 3 minus 1. And so that means that vector u is given by -1 plus 5, so 4 and 2. And then to do the second one, we have our coordinate of 0, 0 as the initial, and then 4, 2 as the terminal. And so in order to get v, we're going to do 4 minus 0 and 2 minus 0, and so we end up with 4, 2 as well. And so they are the same component form. And so they're equivalent, and again, the same vector. All right, then we have something called the magnitude. So that's not necessarily how to get the vector itself. It's actually the hypotenuse of this. How far over and up does it go? So you'll hopefully notice that this is the distance formula, and that's because we're just finding the distance between the 2 points, the starting and the terminal point, initial point and terminal point. Or in order to notate what we're doing, if we have a v as our vector, we put the absolute value signs around it, which does not mean make everything positive, okay? It actually means that you just need to find its magnitude, so it's a new way to use the absolute value symbols. And so if you know the vector, you can actually just take the a value of the vector and the b value of the vector and square them, because that would actually be the same as having subtract them from their initial and terminal point. So again, magnitude is a new use of absolute value symbol, but it does not mean positive or make everything distance to 0. All right, then we've got our 0 vector, and of course it's very hard to imagine, but the idea is that it has no length or direction, because you're not going anywhere, right? It says go no up and no down, and so therefore it is in fact a 0 vector, and so you'll notice that 0 is in bold there. You can have a vector, for instance, that's just vertical, which would mean that it has no 0 going in the horizontal direction. And so just so you know, you can have 0 in both directions as well, and it still potentially exists. I know, it's weird. So in this one, we're going to find the magnitude of u, because the u vector, as we just determined up above, is 4, 2. And so it's going to be easiest if we just take 4, square it, and 2 and square it, and square root. And so we'll get 16 plus 4, and so that's going to be the square root of 20. And you could make that into a decimal, but that is our magnitude. All right, next one. Given vectors u and v of these values, vector addition is going to be just adding the horizontal and vertical components. So officially what you would do is take one and put it on the end of the other in whatever direction it already had, and then your resultant vector is these two together. So resultant. You can also do this way over here, which just takes the one vector and the other vector and then actually meets at the point that if you continued that vector you would make. And this is because it's a parallelogram, so we end up taking this side and then also this side and redoing them, and you create a diagonal of the parallelogram. I don't love this example, and so if you do or don't want to do it, this is the one that Maggie uses, which is me. Alright, so then we also have scalar multiplication, and so what that just means is that there's a number and it's multiplied into the vector. I like to think of it as into instead of by. And so we basically just use distribution. And of course it multiplies the length. So if you had a u, this would be 2u because it's two lengths of u together. You can actually fraction multiply, so it could also be smaller. And then you can actually multiply by a negative, and hopefully you notice that because there is a negative here, it flips it to being going down instead of up. Alright, then we have our unit vectors, and a unit vector is a vector with a length that has a magnitude of 1. So that means that we have this vector, for instance, it's going up at a certain rate. So again, it's going over a certain amount and up a certain amount, but the idea is that we want it only to be a unit length of 1. And so we can have it going in that same direction, but we want to know what is the new vertical and the new horizontal in order to just get that slant length of 1. So, if of course your vector is not a zero vector, because otherwise there's no numbers then, and of course you'd be dividing by 0, which is a no-no, what you would need to do in order to get your unit vector, which would be u in this case, is to take the original vector and divide by the magnitude. So you could do that. Or of course, knowing multiplication, you can take 1 over the magnitude and multiply by the vector. And so that means that each piece of the component form is going to be divided by the magnitude. So, first thing we need to do in this example here is find the magnitude. Otherwise we can't make the unit vector. So the magnitude is going to take -1, square it, and add it to 4, which is squared. And so our magnitude is going to be the square root of 17. And so in order to get my unit vector, I need to take the numbers that we already have and divide them by the the magnitude. If you can simplify, that's cool, but the idea is that you could keep it like that if you needed to. Of course, we don't love having square roots in the denominator, so you can also rationalize that, but yeah, that takes time, and who really cares? Okay. I mean, people do, and probably the answer key will have it, but in this learning moment, that is not our main goal. So again, looking at our formula sheet, the unit vector is here. Again, noticing that c, which was the vector that you originate with, is given its magnitude dividing into the pieces of the component form. We also have the magnitude calculation over here. So we've got that going on as well, of how to get it. And then we have standard unit vectors, which is interesting. Basically, it's just another way to write a vector. And so the idea here is that we actually have an I vector and a j vector, which are your horizontal, because notice that there was no vertical movement, and then your vertical, which again notice that there is no horizontal movement. And so we do in fact have the vector 1, 1, 1 would have been this vector up here. So the vector 1, 4, however, can also be represented by the linear combination, so that's what we're calling this standard unit vector. Linear combination because of this addition here. Looks like a mx plus b is -1 I, again because of the -1 here, plus 4j, again instead of these symbols. So this one's probably going to catch you up a little bit, so just make sure that you understand that this is one way of writing this same vector. And they call it standard form. Alright, and then the last piece is your direction angle, and again this one is going to be on your formula sheet. This stuff here, because this line is going to be in the next unit. So hopefully we've now kind of covered each of these pieces, and so now we know the initial point, terminal point idea here, head minus tail rule, the magnitude, and therefore then the unit vector, and now we're going to go on to the direction angle. So the direction angle of a vector is the angle of a vector in standard position, meaning at the origin. That's actually what that's saying there, angle from positive axis to the vector. And so in order to find this angle right here, all you need to do is take tangent of inverse of the y over the x, meaning the height component over the x component, when we're thinking of it as x, y. The interesting part about this is depending on where you started, we want it to be in standard position, and so we want it to be in quadrant 1. And so sometimes if it is a vector that actually goes down here, you're wondering which angle, like some people will think, oh, this whole angle, but we don't want that whole angle. We would subtract 180, and because we'd subtract 180, we'd be left with that original angle, again, if it had been in quadrant 1. And so again, because of that, you may or may not add 180, or actually subtract, depending on where you are, if the vector points to quadrant 2 over here, or quadrant 3. Because we always want it to be with this line here, kind of at the base of your unit circle. Alright, so we're going to find the direction angle of -1, 4. So, of course, -1, 4 is going to be over here, and so it is not in quadrant 1. It has a height of 4 and a length of 1. So the idea is to get this theta here. And in order to do that, again, since it's in quadrant 2 or 3, and we want to get it back over to quadrant 1 or 2, 1 or 4. This is quadrant 1, this is 2, if you don't remember. Oh wait, that should be IV, not VI. Okay, anyway, Roman numerals. So we're going to take tangent inverse of the y value, which is 4, and the x value, which is 1. We are trying to get a degree, right, direction angle, and so we do want to make sure that we are in degree mode. And if you do this, you get 75.9637. Sorry, I didn't do -1, I did 4. Okay, so we get -75.9638. And so the idea, again, is that we do not want to have that negative representation necessarily, and so if we add 180, we would actually be able to see it in quadrant 1 or 4. You know what, it actually did that for us already, right? -75 degrees is already over here, which would be the opposite of the one we were given. Wow, okay, so anyway, that's our direction angle. And again, the whole idea is once you get it, just make sure that it's in quadrant 1 or 4, and if it's not, then switch it with adding or subtracting 180. Perfecto. So, again, that value, or so that formula is on our formula sheet here. So, if we're going to resolve the vector into components, if V has a direction angle of theta, the horizontal and vertical components of that V vector are found using this here. So again, we're basically going backwards. So we're saying, hey, we know the direction angle, and now we want to find the pieces that would make up that that vector. And so a lot of times they will say, give us 2 points that would be on that vector, or a coordinate that might be on that vector. So in order to find the component forms of a direction angle of 240 degrees and a magnitude of 8, we would fill this in. So magnitude of 8 is going to equal the absolute value of V, and the direction angle is going to be our theta in this cosine and sine. So to find the component form, we would do the magnitude, which is 8, multiply that by the cosine of 240, and then that is going to be in combination with 8 again, but then times the sine of 240. Again, because sine would represent vertical movement, as it does in the unit circle, and cosine would represent horizontal movement, so it would be part of the component form. Alright, and so as long as we're in degree mode, we have 8 times the cosine of 240, and that's negative 4, and then we have 8 times the sine of 240. And that's negative 6.93. And so those would be the coordinates that would be on this vector. Alright, this last example here, an airplane is flying with a direction of 15 degrees at 370 miles per hour. Now the interesting part about this is that magnitude is speed. And so when we think of anything that talks about speed or miles per hour, seconds per whatever, the idea is that that is actually given as the magnitude. So it's got 15 degrees and 370 miles per hour, and the wind is blowing with a direction, oh, well that's not easy to read. Alright, and so it's 235, looked it up, okay. Degrees at 30 miles per hour. So we're going to find the component form of the velocity of the airplane. And then, of course, once we find that, we'll use it to find the actual speed. So let's see what's happening here. So the plane is flying at 15 degrees. So we're going to say that this is 15 degrees. It's a little extra. Not actually. And then it's at 370 miles per hour. But then a wind is blowing with a 235 degree direction. So if we're thinking of this as 0, we've got 180. And then to make it work, let's see, 55 more degrees. So it's going to kind of go back this way. And that is going to be, so this is 55. And then it's at 235. So again, we've got 15 degrees here, and then we've got 235 here, and so our resultant vector is actually this guy right here. And this one has 235, and this one has 370. Now we could use law of sines and all that good stuff, but it turns out we are going to find the component form. Where's 370 was this one. Okay. So we're going to find the component form by just using the previous formula here with your vector times, with your magnitude times the cosine and sine. So let's see. So to find this red vector first, I'm going to do the magnitude, which is 370, and that's going to be times the cosine of 15, and then 370 times the sine of 15. Kind of running out of room. Alright, and so to get that one, let's see, again, degree mode, just double checking that my cosine and sine right. 370 times cosine of 15 makes the first one 357.39, and then 370 times sine of 15 makes 95.76. Alright, and then the blue one, same idea. We're going to do the magnitude, which is 235, and that's going to be times cosine of 30. And then we're going to have 235 times the sine of 30. That's not 30. Oh, I did that backwards. 30 is the magnitude, and 235 is the degree. Alright, so 30 times cosine of 235 is negative 17.21. And then 30 times the sine of 235 is negative 24.57. And so in order to find our combined magnitude, we just need to add them. So we're going to take negative 17.21 plus 357.39 and put that in combination with negative 24.57 plus 95.76. And so our resultant vector component form is going to be negative 17.21 plus 357.39, or 340.18, and then negative 24.57 plus 95.76, and so we have 71.19. So this is our resultant component form based on those two vectors. And so we're going to find the actual ground speed and direction of the angle. And so the ground speed is going to be magnitude. And so we just need to take 340.18, square it, and add it to 71.19 and square it. And take the square root. And that's going to be our magnitude. So apparently the resulting mile per hour is 347.55 of this plane. And so again, it was going 370, but it does have this 30 mile per hour backwards, basically, wind. So we do need to account for that. It's like going uphill. And then the direction angle is going to be the tangent inverse of the y value, which was 71.19, over the x value, 340.18. So tangent inverse divided by 340.18 inside of the parentheses in degree mode is 11.82 degrees. And so that's what this would potentially be. But of course I drew it funky, so. Alright. So your assignment, of course, will be the next video, but that was our set of notes. And remember that all of those are in your formula sheet, so you can reference the formula sheet.